Ryan and Linda are both driving bumper cars with a mass of 300 kilograms. Ryan has a mass of 75 kilograms and an initial velocity of 2,0 meters per second. Linda has an initial velocity of 0.5, 0.7 meters per second. The two bumper cars collide, and after the collision, Ryan's velocity is 1.55, 1.1 meters per second. Assume the collision is perfectly elastic. Find the mass of Linda, her final velocity, and the angle at which she travels. We will define our axes so that the plus x direction is to the right and the plus y is up. With this, we can then draw an approximate picture of the collision. From our physical intuition, we should be able to estimate the direction of V2 final. When we compute our answer, we will compare the direction of the calculated vector to the direction of our initial estimate to see if our result agrees with our intuition. We will now list our known and unknown quantities. We know that the mass of each bumper car is 300 kilograms. We know that the mass of Ryan is 75 kilograms, which together tells us that the mass of the first bumper car is 375 kilograms. We know that the initial velocity of the first bumper car is 2,0 meters per second, and the initial velocity of the second bumper car is 0.5, 0.7 meters per second. Last, we know that the final velocity of the first bumper car is 1.55, 1.1 meters per second. Our unknown quantities are the final velocity of the second bumper car, the mass of Linda, and the angle of Linda's direction of motion. To solve this problem, we will use both conservation of momentum and conservation of energy. We will begin with conservation of energy. We are assuming that no work is done and no heat exchanged between our system and its surroundings. This means that the change in energy of our system is zero, which in turn tells us that the initial energy will be equal to the final energy of the system. The only form of energy in our system is kinetic energy, with each term taking the form 1/2 mv squared. We can multiply the entire equation by 2 to get rid of the factors of 1/2. We can then write the magnitudes explicitly in terms of the x and y components of each vector, leaving us with m1 times the quantity v1 initial x squared plus v1 initial y squared, plus m2 times the quantity v2 initial x squared plus v2 initial y squared is equal to m1 times the quantity v1 final x squared plus v1 final y squared plus m2 times the quantity v2 final x squared plus v2 final y squared. Now we will look at conservation of momentum. Conservation of momentum tells us that since there are no external forces acting on our system, the change in momentum of our system is zero, which in turn tells us that P initial must equal P final. We can split this equation to deal with the components rather than the vectors. Writing our momenta non-relativistically as m times v gives us the following two equations. m1 v1 initial x plus m2 v2 initial x equals m1 v1 final x plus m2 v2 final x, and m1 v1 initial y plus m2 v2 initial y equals m1 v1 final y plus m2 v2 final y. Altogether now, we have three equations with three unknowns. Going through these three equations and labeling our knowns and unknowns, we can see that although it would be possible to analytically solve this system for each of our three unknowns, it would be tedious and time-consuming algebra. We will introduce you to Mathematica's solve command, which can be used to solve systems of equations. In Mathematica, built-in commands start with a capital letter and are followed by square brackets. The solve command takes two arguments. The first, a system of equations, and the second, the variables for which we will solve. Since we are solving three equations for three unknowns, the system of equations will be enclosed in the first set of curly braces, and the unknown variables will be enclosed in the second set of curly braces. We will now enter our three equations. Note that while Mathematica does accept subscripts, I would advise against using them, since they can cause difficulties with variable recognition. Note also that in these equations, we must use two equal signs, not one. In Mathematica, one equal sign is used for variable assignment, whereas two equals are used to indicate equality. The three equations are entered, separated by commas. Then, the three unknown variables for which we wish to solve are entered in the second set of curly braces, also separated by commas. We can evaluate this command by pressing Shift-Enter. Mathematica outputs a symbolic result, solving for our three unknowns in terms of our known variables. As you can see, this symbolic result is complex and unwieldy. We can get a simple numerical result by asking Mathematica to evaluate this using our numeric values for our known variables. We do so by inserting between the closing curly brace and the comma separating our set of equations from our set of variables, a / followed by a period, followed by a set of curly braces. Inside these curly braces, we will put the name of our known variable, a dash, and a greater than symbol, indicating an arrow pointing to the value which will be assigned to that variable. We will input that M1 will be evaluated with a value of 375, V1 initial X 2.0, V1 initial Y 0, V2 initial X 0.5, V2 initial Y 0.7, V1 final X 1.55, V1 final Y 1.1. Pressing Shift-Enter again re-evaluates this statement with the new information. Mathematica gives us numerical results for each of our three unknown variables. We find that M2 is equal to 358 kilograms, which tells us that the mass of Linda is 58 kilograms, and that V2 final is given by 0.97, negative 0.45 meters per second. Looking at this result, we see that it points in the positive x and the negative y, which agrees with our initial estimate from our drawing. We can solve for theta, the angle of Linda's trajectory, using trigonometry. We can see that V2Fx is adjacent to theta, while V2Fy is opposite. Thus, theta is given by the arctangent of V2Fy over V2Fx. This gives us an angle of 25 degrees relative to the horizontal. Lastly, we will perform our sanity checks. One of the many advantages to using Mathematica's solve command is that if the equations which you input are all dimensionally correct, your results will be dimensionally correct as well. For our order of magnitude check, we see that the mass of Linda is in the same order of magnitude as the mass of Ryan, and that Linda's final speed is of the same order of magnitude as Ryan's final speed. Lastly, our calculated results agree with our initial estimate, which was based on our physical intuition.